Hello, I'm Csomay-Shanklin, and I'll be presenting on multi-rate planning and control of uncertain nonlinear systems, model predictive control, and control Lyapunov functions. This is joint work with Andrew Taylor, Ugo Rosolia, and Professor Aaron Ames at Caltech. We'll begin with the broader motivation of multi-rate control, a control architecture composed of different levels, where each level may use varying model approximations and be running at different frequencies. For example, the low-level controller may be a nonlinear feedback layer running in real time, the mid-level a discrete time trajectory optimizer, and the high-level a decision-making layer. One primary motivation for studying such a framework is that in practice, control algorithms are often implemented hierarchically. For example, all of these robots that I have worked on in the lab employ some form of hierarchical control, specifically some feedback control layer paired with a mid-level trajectory optimization layer. So, there is a need to develop and explore the theory that reflects this structure, and specifically to investigate the interaction and information flow between the layers of the hierarchy. In this work, we will consider the interaction between the low and mid-level controllers. Here, these take the form of control Lyapunov functions, CLFs, and model predictive control, MPC. The benefits of using control Lyapunov functions is that they provide constructive, robust stability guarantees for nonlinear systems. At the same time, using only CLFs results in myopic or short-sighted decision-making and are difficult to integrate with state and input constraints. On the other hand, model predictive control is a powerful tool that provides optimality over a horizon and is able to naturally incorporate state and input constraints. However, computational limits necessitate the use of model approximations such as reduced order models, or in the case of this work, linearized and discretized models. The goal of this work is to take a step towards combining the benefits of both of these frameworks into a unified architecture with guarantees. We'll begin by discussing the design of a feedback controller, which will be focused on quantifying how well trajectories can be tracked at the low level. Then we will transition to the mid-level and discuss producing trajectories and satisfying state constraints, followed by satisfying input constraints. We'll conclude by putting all of the pieces together and discussing results. We start by considering the class of systems of the following control affine form with disturbances. We make the assumption that 0 is an unforced equilibrium point and that the actuation vector is non-zero for all x. Note that the system is single input, single output, and in block integrator form. The presented tools are readily extended to MIMO systems, and the restriction to CISO systems is simply for ease of exposition. Also note that this assumption and structure is satisfied for full-state feedback linearizable systems, for example by finding an appropriate output diffeomorphism, and is made so that the system in question can follow quote-unquote arbitrary trajectories. What we mean by arbitrary trajectories is the class of dynamically admissible trajectories, or in other words, the trajectories for which there exists a control input satisfying the dynamics. For example, given 2 points in the state space, a linear interpolation would not be dynamically admissible, but some other interpolation may be. These trajectories must be possible solution curves of the system. We now have 2 questions. 1, how do we synthesize these trajectories? And 2, how do we track them with disturbances? We will start by addressing the second question, and we'll leave the first one for the next section. Consider the dynamics and associated vector field of the system in question with some control input u. Given a dynamically admissible trajectory, we can define an error signal E as follows. Under the previous assumption, there exists a feedback controller such that the error dynamics are rendered to be a stable linear system. Then, we can construct a quadratic Lyapunov function certifying this stability via solving the continuous time Lyapunov equation for a matrix P, whose time derivative will satisfy the condition for exponential stability. Using this Lyapunov function, we can synthesize a quadratic program-based controller, which will meet the desired rate of convergence, but may be less intrusive than the previously designed feedback linearizing controller. When disturbances are present, we may no longer be able to converge to the origin, but using an input-to-state stability argument, we are able to constructively produce a constant C, which is a function of the magnitude of disturbance such that any state outside a Lyapunov level set lower bounded by C exhibits exponential convergence. Then, we can state that under the CLF controller, the solution to the closed-loop dynamical system phi will lie in the sublevel set E of the Lyapunov function. This should feel like it's going in the direction of tube MPC, where E represents a robust invariant for the nonlinear system. In fact, this work is an extension of tube MPC, a form of robust MPC, which we will go into more detail coming up. Now that we understand what it means for a trajectory to be dynamically admissible and how to quantify how well it can be tracked, we will shift to the mid-level and discuss how to produce such trajectories while satisfying state constraints. The goal of this section is to keep the flow, phi, of the closed-loop system inside the state constraint set X, and the approach will be to keep the desired trajectory, Minkowski summed with the robust invariant from the previous section, in the state constraint set. Specifically, given an initial condition, a terminal condition, and a discretization time t, we want to produce a dynamically admissible trajectory connecting them. To achieve this, we will employ Bézier curves. Bézier curves are defined by a collection of control points and are constructed as the inner product of these control points zeta and Bernstein basis polynomials z. Given boundary conditions, we can construct a curve of order 2n-1 connecting them by solving a matrix vector product, where the matrix D is known a priori and is only a function of the discretization time. Furthermore, we show that a curve produced in this way is dynamically admissible. Bézier curves enjoy a number of desirable properties, such as that the derivative of the curve can be represented as a Bézier polynomial of the same order whose control points are linear in the original control points. Again, the matrix H is known a priori and is only a function of the discretization time. Also, the continuous time curve is contained in the convex hull of the control points. This will allow us to make conclusions about the curve by reasoning only about a low-dimensional finite collection of points. In the case of disturbances, we can only track the produced curve within the previously defined tube E. Going forward, we assume the set X is a compact convex polytope. We show in the work that if the control points lie in the state constraint set shrunk by the robust invariant E, then the closed loop system will remain in the state constraint set. This again is a tube MPC approach to robust planning. Furthermore, we show that the constraint is affine in the control points zeta. Later, the control points will become the decision variables in our MPC program, so ensuring that the constraint is efficiently representable is of significant importance to the tractability of this formulation. Now we are on to the input constraint section, which deviates from the standard tube MPC approach and requires a bit more machinery. We will omit some of the details for the sake of time, but if you're interested, then I encourage you to read the paper, and I'm happy to talk further about it to anyone at any time. The goal of this section is to bound the norm of the control input required by the low-level feedback controller by some maximum value. The approach that we will take is to sandwich a convex function of the control points zeta, which when upper bounded will bound the low-level controller. We'll start by massaging the form of the low-level controller by adding 0 and using the triangle inequality. Then we can use the optimality of the CLFQP to reintroduce the feedback linearizing controller, which has a convenient structural form as shown here. Then, using norm inequalities, we will end up with 3 terms that need to be further investigated. Letting x bar k be a reference point in the set X, and xd of t, the desired trajectory evaluated at a point in time, we start with the actuation vector by again introducing terms that we would like to see, specifically the desired trajectory and the reference point. We proceed by employing Lipschitz, where 3 terms show up: the tracking error from the low-level controller, a trust region, or how far the desired trajectory will deviate from a reference point, and the evaluation of the function at that reference. The general approach here is, in order to bound the function g inverse at a point x, we can instead bound its evaluation at intermediate points that we know what the value will take. Looking ahead, we will be able to replace the desired trajectory with the control points, giving us a tractable way to satisfy the bound on the above norm. We can do the same procedure for the drift dynamics, and we know that the error signal is bounded by a constant e bar from the properties of the low-level controller from before. Here we have copied over the 3 bounds from before, and with some reorganization, we get the following quadratic form out. The term sigma is a trust region, expressing how far the desired trajectory and its dynamics veer from a reference point x bar, and m, n, and gamma are functions of the Lipschitz constants from before and properties of the low-level controller. The exact structure of m, n, and gamma are not so important. So to avoid confusion, the important elements are summarized here. In line with our original goal and the above approach, we will try to bound this expression by some maximum value. An example of the region of admissible states where this bound holds is depicted here. There are presently 3 issues with achieving this as stated. Specifically, it is not convex due to the structure of M. It requires knowledge of the Lipschitz constants, which are difficult or impossible to estimate in practice, and it needs to be enforced continuously in time. We will address each of these concerns separately. First, we can uniquely project the matrix M onto the positive semi-definite cone. This tightens the feasible set, but it respects an ordering in the sense that if we enforce a constraint with this matrix, it will be enforced for the original one as well. Doing this operation makes the above constraint convex in XD. Specifically, it is enforceable as a second-order cone constraint. Next, we can replace the Lipschitz constants with tuning knobs. Specifically, in the work, we show that the values of M, N, and gamma as a function of the parameters alpha and beta satisfy a monotonicity property, meaning that for sufficiently large values of alpha and beta, guarantees are preserved. This is a useful development because this gives some degrees of freedom in the design process, and in practice, desirable performance may be achieved long before the true Lipschitz constants would predict. Finally, we address the fact that this condition needs to be enforced continuously in time by first observing that this truss region we introduced is bounded by the supremum over all of the control points of the desired trajectory. Then, if we enforce the following second-order cone constraint, the constraint on the original expression is enforced, and by extension, the norm of the feedback controller is bounded by the maximum input as well. Now that we have addressed all of the issues, we are left with a convex constraint on the control points, which can easily be added to the MPC program, as is done in the next section. Okay, now we are ready to put all the pieces together and demonstrate some simulation results. The complete MPC program is as follows. We minimize a quadratic running and terminal cost subject to various constraints, including the linearized dynamics, a relaxed initial condition which mirrors that of tube MPC to ensure recursive feasibility, a terminal constraint, constraints regarding the construction of dynamically admissible trajectories and robust state constraint satisfaction, and finally, input constraints. This is the combined multi-rate architecture in final form. From the previous developments, note the Lyapunov level set that the low level passes to the mid-level, and the desired trajectory that gets passed back down to track. Here's an example system where the MPC layer is running at 1 Hz with no disturbances. Just employing a CLF at the low level, as shown in red, state constraints on the left and input constraints on the right are violated, but stability is maintained. Just using a mid-level controller, as shown in green, we see that compounding linearization error yields instability and violation of constraints, whereas the proposed framework in blue is able to satisfy both state and input constraints while ensuring convergence to the origin. It is interesting to note the slight deviation from the feed-forward input that the proposed method uses to track the trajectory while still remaining in the input constraint set. Now we run the planning at 10 Hz and introduce bounded additive disturbances. Again, we see that only the proposed methodology is able to satisfy the state constraints, while just using the low or mid-level independently results in a violation. Finally, we look at the behavior of the system when we increase the tuning knobs presented before, which are meant to emulate the Lipschitz constants of the system. As the knobs are turned up, it represents the low-level controller requiring more input to be able to track the desired reference trajectory. In response to increasing gains, we can see on the left that the planning level naturally puts the optimal trajectory points closer together spatially to limit the resulting linearization error and, by extension, the deviation from the planned input. On the right, as it does this, the deviation of the low-level controller from the planned input is reduced. In summary, we have developed a multi-rate architecture which integrates CLFs and MPC for robust state and input constrained nonlinear stabilization. Also, we use the convexity properties of Bezier curves to enable tractable online planning with guarantees. Future work is multifaceted and includes extending this work to the sample data and MIMO settings, as well as addressing systems with under actuation, adding a high-level decision-making layer, and demonstrating this technique on hardware. Thank you very much for your attention.